Okay, so my name is Deepak Cherian. I'm a postdoc with Emily Shroyer and Jim Moom at Oregon State as part of the Ocean Mixing Group. Today I'm going to talk about some work I've been doing for the past 2 years, looking at turbulence data from the Bay of Bengal. So all of this is funded by ONR, so thank you. And I'd also like to thank Hemanta at NRL, as well as people at NOAA PMEL for deploying our instruments on their moorings. The instrument I'm going to focus on is this one in the center. So Rita Brett's talked about it a little bit, but it's called a Kipod. It was built by Jim Moom at OSU. And the main instrument on here is this sensor, which is a fast thermistor. So it records temperature fluctuations at 100 hertz. We take that 100 hertz time series, add a lot of turbulence theory, and come out with a 10-minute time series of turbulent diffusivity and turbulent fluxes. And so those are the two quantities I'm going to focus on. As part of a series, Kipods are deployed at many different locations in the bay. So Rita Brett talked about the Hui mooring. That was at 18 knots. I'm going to show you a little bit of data from the Rama moorings. That's at 12 and 15. But really spend a lot of time talking about these three EBOB moorings at 8 knots, right? And in terms of depth, so at the Rama moorings, here are Kipod depths in horizontal lines, put on top of Argo climatological profile. So you can see at 15, 30, 45 meters on the Rama moorings, we are in the mixed layer, the barrier layer, or somewhere near the base of those two. At the EBOB moorings, on the other hand, we are in the thermocline. These moorings moved up and down. They were subsurface, so they moved up and down by 50 meters-ish. And so that kind of depth coverage is shaded here, right? So it's going to be a lot of data from the thermocline. And so point one from a year's worth of data to say is that there is a seasonal cycle in diffusivity. And to illustrate that, I'm going to show you two time series, one from 50 meters and one from 100 meters. The first top panel here is wind stress in black, net surface heat flux in color. So red means you're warming the ocean, blue means you're cooling the ocean. And so you can see the kind of monsoonal cycle that we've all been talking about, right? So there's moderate winds, no winds, high winds, and then cyclones, right? And surface flux is also kind of sensible. Down here is something interesting, which is daily average diffusivity from the 50-meter mooring and 50-meter Kipod that was at Rama 12 knots. So this record's already been shown in Sally's paper, so I'm just going to go through it quickly. But the point is, you have moderate winds, you have diffusivities of 10-4 to 10-3. The winds die down, you have net surface heat flux. The Kipods are now below the mixed layer in stratified water. Diffusivity drops by 2 orders of magnitude. The winds pick up for the southwest monsoon, diffusivity goes up, stays high, we're sitting in the mixed layer. The winds die down, and you see these two big cyclones, and we see big peaks in diffusivity, right? So all of that's really nice, and as Rita Brett showed, if you scatter KT against wind stress, you get pretty good correlations. It's the same story at 18 knots, 12 knots, and 15 knots. More interesting, though, is this record from 100 meters. And so now, in this case, all of our values are much lower, right? So we are sitting at about 10-6 during the northeast monsoon. In April, everything dies at this record. There's literally no turbulence seen by our extremely sensitive instruments. During the southwest monsoon, mixing goes up, but again, we're still talking only about 10-5-ish, right? So this is still relatively low in the scheme of things. We had one big mixing event where KT went up to 10-4-ish, and that was coincident with the near inertial wave burst that was going by the Kipod. And then in October, November, we started to dip down and again go back to no mixing with some isolated bursts, right? And so a big focus of my talk is going to be this kind of record. And I just want everyone to keep in mind that at 8 knots, you have the summer monsoon current bringing in salty Arabian seawater. And so at this mooring, it was present roughly between July and the middle of December. And so I've shown you seasonal cycle in two time series. Here's the same seasonal cycle shown in terms of vertical profiles. So somebody was asking about this. What I've done is taken all of our data across the bay, bin them in isopycnal space, and then average them in seasons to get means and medians. And I locate them on a vertical profile at the kind of rough approximate vertical depth of that isopycnal bin. So you can kind of it's a sensible way to construct a vertical profile. So in red are medians, blues are means. And so again, just quickly, the point of this figure is to say that the seasonal cycle that I showed you as part of the time series is common to all other moorings, all our other instruments, right? So in the northeast monsoon, medians are really low. You have some highs, so it means we have some isolated events of high mixing. During March and April, both means and medians are really low. The bay is extremely quiet in the thermocline. The southwest monsoon means and medians both go up, so this is a period of generally high mixing. The distributions in the southwest monsoon are very different from that in the northeast monsoon. In October, November, you see, it's kind of confusing, mostly because a lot of our instruments die, so these are not as well sampled as the other bins, right? But we still have high mixing. And so why do we have this seasonal cycle of mixing? So I started off trying to look at Richardson number and reduce shear. This didn't work out so well. I think it's because all of our mooring observations are a little coarse. So we're looking at shear on the scale of 20 meters, n square on the scale of 20 meters, and shear measured hourly. So those quantities didn't make too much sense. Instead, what I've been trying to do is to say whether we can make a statement about what components of shear are contributing to mixing, right? So I'm looking at near inertial shear, which I've calculated by taking a shear time series, band pass between 2 and 7 days. And then low frequency shear, which is a low pass at 10 days. And the reason I picked these two is because if I look at variance preserving spectra of the shear, those are the two biggest components. What's left is quite tiny. And so these are now two-dimensional PDFs, kind of. Not even really. It's like two-dimensional means. So in color is diffusivity. So if you see white, that's 10 minus 6. Really dark colors are 10 minus 4, and then there's variation in the middle. Each panel is a season. On the y-axis is near inertial shear squared, right? So calculated using the bandpass time series. On the x-axis is low frequency shear squared, again calculated using the low pass shear. And so for each of these bins, I take all of my observations at 8 knots and average them, right? And then color them by KT. I've put a 45-degree line so that if you're along the line, it means both components of shear are kind of equally important. So let's start up there. So the northeast monsoon, you see kind of low mixing for low values of shear, and most of the high mixing values are in the upper triangle. So that means near inertial shear is much larger than the low frequency shear, right? Similar story in the northeast to southwest transition. All our high events are usually up in the upper triangle. So I was telling you that at least in the first half of the year, anytime we see high mixing, we also see high near inertial shear. The summer monsoon is really interesting because now you have this ridge of high mixing that's in the lower triangle, which is telling you that you're seeing mixing events that are coincident with high low frequency shear. So this is the presence of the summer monsoon current that's kind of meandering through 8 knot at this point. We still see some high mixing events up here. So the near inertial waves are still coming down. It's the southwest monsoon, so we still see some mixing there. The kind of cyclone season is kind of weird because now I'm seeing high mixing values generally at lower values of shear and kind of no mixing at higher values of shear. But the thing that's missing here is stratification, right? It also matters where you are in the water column relative to stratification. So I don't think that's too crazy. But in general, we're seeing higher mixing coinciding with higher shear. The last point I want to make in this figure is this kind of general covariation of the low frequency and the near inertial shear squared, which I thought was really interesting. I don't know why. But question from Lou?
Yes, so the why the normal way
because I was trying to pick these two components out. So then this is everything. So it's between 50 and 100 meters at 8 knots. So there are 6 different chipods in there. So I'm trying to split the, I'm trying to do this. So the problem is, anyway, the problem is if you start to do n squared and any kind of reduced shear thing, it doesn't really make much sense because I think of how we've sampled it. So just kind of zooming out to like big picture there, right? So I'm talking about the southwest monsoon. On top is EKE in color and Oscar surface velocities. And this is kind of coming to, again, what I've been saying so far is our mooring line at 8 knots sees the summer monsoon current come in. It's easily visible as an EKE maximum, right? So it's meandering and you have the Sri Lanka dome and all of this stuff that's happening. And for the last bit, what I really want to talk about is this idea that if you think about the salinity structure of the bay and the salt budget of the bay, we have fresh water coming in and it's exiting on the east and the west. But at some point, you need to be mixing salt upwards, right? And so there's this idea from Vinay Chandran 2013, which is that the 35 PSU isohaline is shallowest in the southwestern bay. So as a version of that, I'm showing you 34.75, mostly because that's what we sample. And this is the depth of that isohaline calculated from the gridded Argo data set for the southwest monsoon. And so if you look at this, you see this little tongue here where the salty water is basically really close to the surface, right? So it's 50 meters, 75, and 100 meter depth. So it's kind of near the surface here, and it's deeper in the northern bay. And the point to take out of this figure is that this isohaline, or the Arabian Sea water, is shallowest in the water column between July and December. And so now if you take that piece of information and you stick it on my vertical profiles, so the same profiles I showed you earlier, but now with the depth of that isohaline, again calculated from Argo, you see that it's slowly changing by about 30 meters. But in terms of the mixing that the isohaline sees, that's extremely different, especially in terms of the median that isohaline sees, right? And so this means that there is a possibility that our instruments have resolved, or at least have some estimates of the vertical flux of salt out of Arabian Sea water into the fresher Bay of Bengal water, right? And so how do you estimate that? The way I do it is to take hourly average diffusivities, multiply it by a local gradient, and I'm showing you all of the points throughout the year at 8 knot in the top panel as a function of depth and time. And so you can see the complication with this, which is we start off with all of our instruments at kind of regular depth. In July, as the summer monsoon current comes down by, all of our instruments dive down under the region of greatest shear, but then they're kind of stuck there. They see some high mixing events, and they kind of go back up. The way I make sense of this is to transform to salinity space. Again, the same points, now with salinity on the y, and again in time. And I've been between 35 and 34.5 saying that, well, we have observations basically throughout the year, right? In that bin, I can bin average to get a monthly mean estimate of salt flux out of Arabian Sea water mass. And so that's in red here. And it's kind of interesting, you see kind of a small amount of flux, no flux between February and July, starting to see some more flux, peaks in September and October. Value is roughly 2 times some units. I'll come to that. For some reason, there's nothing November, more in December. And so this number is only meaningful in terms of something to compare it against, right? And so what I've shown here is kind of virtual salinity flux at the surface. So that's S naught times E minus P in blue. And the point to take away is this height is order of magnitude, is really close to this height, right? So that's one comparison. It's telling us that the upward turbulent flux of salt is kind of the same or magnitude as the stuff that's coming down. The other thing you can compare against is this number from the salinity budget of Wilson and Reiser. So they do a budget, it's an Eulerian budget, so they take the top 30 meters of the water column and say you need 2 to 4 times 10 minus 6 that's coming up. And so since it's Eulerian, it means that that's advection plus turbulence. But my number looks like 1.5 to 4 times 10 minus 6 in roughly the same time frame. It's deeper, so it's between 70 and 100 meters, but it's at this particular isohaline. I don't have an advection estimate yet, but Debasis has given me some ideas. And that's where I want to end. It's with this, it's that our numbers are really close to each other, and it looks like we're seeing significant turbulent fluxes up into the Bay of Bengal. Thanks.